Everyone, thank you very much for coming to this session. I'm Ravi Diaz. I'm from University of Rochester. I'll be discussing our recent work on the ambient condition superconductivity and national doped lutetium hydride. So just before I start to talk, I would like to acknowledge the people who behind this support this work. This is my group as of spring 2023, and this is my colleague Aslan Shalamat from the UNLV who work on these materials. And I closely work with the Silverberg group at Harvard, and as well as from Stanley group at UIC, and the college group at LE, and Zurich at Buffalo. So, of course, we use HV-CAT group here as laboratory for characterizing this material, and I would like to acknowledge the funding agencies as well. All right, the superconductors. So we all know about the superconductors and what it can do, right? We heard about it very well starting from the first discovery. So, but all this time, the temperatures are very low temperatures, but it, because of that, it did not live up to the height, the promises. So imagine if you can have an ambient condition superconductor. So I can categorize three different directions. So for the first one is it can be helpful for quest for fusion, the magnetic confined fusion. So the limitless, cleanest form of energy can be viable having an ambient condition superconductor, as well as electronic devices, your phone, your laptop, that can be dramatically increased. Of course, transportation, you all heard about it. Is anyone a fan of the Back to the Movie Future? Boards? Yeah, here we go. So those things can be possible there. So the promise is huge. So, but because of the low temperature phenomena, we didn't release in the actual application. So my talk is going to be the special type of material to follow the conventional nature of the superconductivity VCS model, reaching to the ambient condition superconductor. All right, so let's see. So the pressure is a tool that we are using. So we all seen that in these talks that pressure really dramatically impacts on the material properties. So you can change the nature of the properties of the material. So this goes back all the way to 1925. Already after discovering the superconductor, you see the mechanical pressure can change superconducting properties. So fast forward to 7 years, two breaks. So the new type of material absorbed in the 1980s and then enhancing the TEC with applied pressures based on the chemical pressure. Of course, then if you look at the ion-based superconductors, at the same impact as well. So the pressure being really a tool that we can change the nature of the material. So then when this new type of material comes to the picture, is superhydride, so-called. So this goes way back to the prediction of metallic hydrogen. So 1968, Neil Aspel, the late Neil Aspel predicted that metallic hydrogen, if you come to the metallic state, it could be a room temperature superconductor based on simple VCS model. So, but the pressure that required for it there is enormous. So the practical scene that is kind of hindered until recently. But then, 2004, he came up with a very similar idea that probably hydrogen-dominant alloy would only be the best way to approach that, to mimic the same metallic hydrogen properties, but at much lower pressures by using different dopant in the system. So that's 2004. So this is remembering later Neil Aspel to all these discoveries in this field is based on his earlier predictions. So I would like to mention one of his quotes from the 2010 GRC, whatever it is cool into, whatever it is squeeze it. All right, with that, this superhydride, there are two different directions that you can go. Probably you've heard about this as well, covalent type hydrides as well as metal dope hydride. So let's see the progress. I'm going to start with the theory. So the theoretical prediction, for first theoretical prediction for these claptrate-based beautiful structures for superconducting as high as 235 Kelvin and under pressure predicted by Yang group and calcium hydride. And then later we see the lanthanum hydride and yttrium hydride from Russ Henley group, and such this very soon after that there was another prediction from the Cambridge group and the Yang group. Again, this rare earth metal hydride in solution to mimic the same hydrogen superconductivity at much lower pressures. Since then, there are a lot of theoretical works from the Zurich group and the Gori, there were Ion Herrera from Spain. They have studied these extensively, this material with antiharmonic effects and everything. So there are a lot of theoretical works. So let's see the experimental progress. So the pressure and temperature. So we were at here, ambient pressure, ambient pressure, and this is the low temperature, all these material as superconductor. This is where we want to go. And metallic hydrogen, produced in 2017, they have right here 500 gigapascal, which is predicted to be a room temperature superconductor. But if you look at the pressure, as you know, this is 500 gigapascal. So the idea is to use this same metallic hydrogen idea to bring it down via using the chemical pressure. So the first of that kind came in 2014 by Erick's group for hydrogen disulfide. And in 2019, lanthanum hydride from our Henry group. And in 2020, from our group, the carbonaceous sulfur hydride, reaching room temperature. And then the 2021, yttrium hydride. And then recently, again, carbonaceous sulfur hydride via carbon tuning. We were able to bring it down the pressure from 100 GPa. So this is where we are. So the point that we want to get to is ambient condition right here. So I'm going to introduce a new material for the first time. We have another rare earth hydride called nitrogen doped lutetium hydride. It's a lutetium hydride doped with nitrogen. This is a blue color sample at ambient condition. But if you apply pressure, so start with the blue, apply pressure about 3 kilobar, it turns into a pink. It's a very bright pink color. And then if you further squeeze it, it becomes bright red. So this material, this remarkable material, shows the superconducting properties when the color changes from blue to pink around this pink region. So let's see in simple terms, how do you detect superconductivity? So there are three main features that you can use. At the previous talk, you heard about this magnetic measurements. So the three main features you can do is the electrical resistance measurements, Mason effect, showing that one, and heat capacity. Within these, you can have some measurements of the magnetic field studies, magnetic susceptibility or magnetization curve, or again, the field studies. These are the very basic three different evidence that you can provide. So what I'm going to show you is that I'm going to provide the evidence for all these three different measurements in this material called nitrogen doped lutetium hydride. So the first one, so electrical resistance measurement. So what you're seeing here is that conductivity measurement with a function of temperature. The first one, you see the blue color one, 10 kilobar, TC is as high as 294 Kelvin. The blue one right here, you see drop in electrical resistance to go to 0. So the right side axis belongs to this blue color curve right here. And then you see two more pressure points, 16 kilobar and 20 kilobar and 269 and 251 Kelvin. Applied pressure, the suppression of the TC over there, and also you see the boarding of the transition to the pressure board. And the insert, what you're seeing here is the picture of the sample with the electrical leads to measure the conductivity properties. So, defining the TC, different groups take onset or midpoint or the minimum value. All these values that we reported in our discovery is the onset of superconductivity. So, of course, one of the questions, the easy question to ask is that how do you know that you're going from a metallic state to another metallic state, not a superconducting state, right? So, for that, what you can do is you can study the IV curve. So, if you follow this is a simple metal, you should follow the basic, it should be linear behavior, this proportion should be I, right? Let's follow the Ohm's law. So, what you see right here is the very nice linear behavior before it's superconducting at the normal state. But while it's superconducting, you see this nonlinear behavior. You shouldn't pick up any voltage, it's just a noise, or maybe at the end it's cleaning it out, see this nonlinear behavior. So it's not going from another metal to another metal. So this is another example, another pressure point, 6 kilobar, TC of 240 Kelvin. So again, pay attention, it's the kilobar pressure, not in gigapascal. So 6 kilobar. So you see the nice linear behavior before, and after that you see the constant behavior. Alright, that's the first evidence. The second one is the magnetic measurements, magnetic susceptibility. So you can do DC measurement, you can do AC measurement. So first I'm going to show you the AC susceptibility that we do. We use a very standard technique, two-coil system. This is the schematic diamond and two-coil system, primary coil and the dummy coil. So the signal is basically the difference in primary and dummy coil. And then of course you have your sample right here in the coil that add into it. In ideal case, your background, so the background from primary and dummy is same. cancel out. So you get some, that's the ideal situation. But in the experimentally, you have background. We call it balancing the coil, but we can't really balance it all the way to zero. There was always some value there. So I'm going to show you one graph right here. What you see is with the temperature, superconducting transition on this red lutetium sample, cool it down, you see dropping signal here, but you see this background rising. So there is always a background. So you have to subtract it out to see the ideal situation. So the 0, 0, you see the once you subtract out this background polynomial, you see this graph. Again, this is for purely a visualization process. You know, you can see this one even without background subtraction, this sample, right? The signal is right there. And this is you done for just for the purely visualization process. So what we have done is we have done the AC susceptibility for different pressures. These are 3 different pressures that we are showing you, 10, 16, 22, with the TC as high as 294 Kelvin. So this is the AC magnetic susceptibility. And we have done the DC magnetic susceptibility as well, the true representation of the Mason effect. You see the shielding, zero field cooling and the field cooling. So showing the diamagnetic response from the DC measurement as well. And then thirdly, we have done the image curve as well, so magnetization curve to see this diamagnetic response. So that's the second technique that we use to prove the superconducting transition. So the third one is the heat capacity. So we have developed a new method to measure the heat capacity under pressure. So one of my students later will explain the technique. So we use MgV2 as our test sample to see this at similar pressures, the transition after changing in the heat capacity signal. And we have done that for our new sample, lutetium hydride, nitrogen dope. You see in the nice transition at 290 Kelvin and 245 for 2 different pressures. So in summary, so you see the superconducting transition as high as room temperature at 10 kilowatt, and this is when the sample becomes a pink color material, blue to pink to red. This is where the high superconducting you can see. So this is also very closely goes with the color change, and the stability range is 3 to 32 kilowatt. So if you look at the summary in our progress, we are right here with hydrogen. This is where we wanted to go, metallic hydrogen, 2014 H3S, lanthanum hydride, carbonaceous sulfur hydride, yttrium carbonaceous, now lutetium, we are right there. We are very near ambient conditions, now we can use a different technique, and so as well. So this is the start of the new type of material, using this for practical application. Now it's in the range that we can use for strain engineering or different techniques to use this one for application as well. So with that, I'd like to thank as a support for the NSF.